So thank you for joining us today for our water utility case studies on non-revenue water reduction. We are really pleased today to have guests with us. We have Gus Father from King County Water District 90. They are just outside of Seattle in Washington State. And we have Scott Donnell from the city of Waterloo, which is just about half an hour from where I'm located in Guelph. So that's great. Gentlemen, thanks for being with us today.
Yeah.
We also have Stan Fong, our CTO. Stan will be leading the webinar for the most part and working through the slides. And we will take question and answers either for Stan, if I can answer, I might try, or for Scott and Gus. They'd be happy to jump in and answer questions at the end of the presentation. So thank you for joining us. I'm going to turn the presentation over to Stan and Gus to get started. We're going to dive in just outside of Seattle, Washington, with our first case study for you.
Sounds good. So we'll give Gus a chance here to kind of walk you guys through their system, challenges that they're working through right now, and then we'll dive into the leak detection side after that.
Okay, so I guess I'll start by just kind of explaining where we're at. We're located in King County in Washington. Like Tim was saying, we are kind of in the East Renton Highlands area, if you're familiar with that area. The majority of our district is in unincorporated King County, but we border with Renton, which is a fairly larger city next to us. We currently have roughly 8,200 meters service connections, however you want to quantify those. And that equates to a little over 20,000 residents in the district. Our supply that we primarily purchase water from a local utility, Seattle Public Utilities, and we produce a small amount of water right now through groundwater wells that we maintain and manage in-house. But as far as our system goes, we're made up of all different types of pipe, anywhere from our newest HDPE all the way back to tar wrap steel from probably the 60s or early 70s. You can see on this slide how much left of the older pipes that we still need to replace, which is kind of a daunting task for us to try to figure out how to do that. With 20,000 lineal feet of steel is kind of what we're tackling right now. Every year we're putting out projects to replace those. And then in the future, we will be going to AC. And then after that, cast iron, and then eventually, hopefully not in my career, but the ductile iron that is still in the system, with the goal of being 100% HDPE in the future, is kind of where we're going for. Kind of the techniques and the reasons why we reached out to Digital Water Solutions and looked at that is we're pipe bursting. So for us to replace the amount of water that we have to do as quickly as we can and as cost effectively as we can, we chose the pipe bursting method. So that seems to be working out well for us as far as cost per foot of install. But that kind of leads into the next slide for Stan, if you wouldn't mind switching to the next slide. These areas are AC water mains in the district, and some of the highlighted areas that we want to get into with pipe bursting. The problem that we're having with pipe bursting AC in this Puget Sound region is that pipe bursting right now has not been approved as an effective method or a safe method to replace that type of water main. The local authority that comes up with the laws and regulations in our area has said that the AC asbestos concrete main or asbestos cement main, we're not allowed to pipe burst it. So in the meantime, while we're pipe bursting other types of material and replacing water mains, we wanted to find out and figure out a good way to monitor these large areas of AC main that are fairly fragile, that we have, consistent leaks with each year. we wanted to find out a good way to monitor them. And so that kind of led us to digital water mains or digital water solutions with their hydrant sensors. So as far as that goes, I think these are the different phases that we're looking at. We've already got our system in phase one, and then we're communicating with them right now and looking at potentially getting out into phase two, which is a lot larger area, and it's going to take more sensors to them. But I think for that matter, I think Stan, I think you can take over from here.
All right, thanks, Gus. Appreciate the background. So as Gus kind of alluded to here, we've done phase one already with the sensors. And what we really want to look at today for both King County and City of Waterloo is what does the first year look like, right? When you start a monitoring program. So before I dive into the actual pilot area itself, I just want to go over kind of a rough timeline, right? So what it looks like for those that are not familiar, when you work with digital water and you're installing Hydrant.ai, we look at it kind of a little bit more than a year because what happens is prior to that monitoring program, the start of it, there's a planning phase, right? So we're meeting with utilities, we're trying to understand the key drivers, we're mapping out where to put these units based on those drivers, and then we come up with, okay, this is the area, this is where we're going to install the units. You get that strategy going. And then obviously install the units, we start collecting that data. And the first thing we do is we look at the acoustic data from the unit. So we're collecting acoustic data, pressure data, temperature data. But what we do that's unique to us is the pre-existing leak detection, meaning that there's going to be leaks often in these areas, especially if you're dealing with a lot of breaks historically and non-revenue water is an issue. There's going to be leaks already in there in the present baseline data. So that's often missed when you use a traditional kind of logger solution, things like that. They just look at the baseline as it is when you install it. And then if that changes, it goes up with a new leak, you can find that new leak. But any leaks that are already there, they kind of just exist and they're just going to stay there and continue to contribute to that issue until they actually burst or they grow in size. So the first thing we do is right from the get-go, we look at that acoustic data and we see, can we provide something to the utility that they can use to get out there immediately from day one almost and find these leaks. And we're going to see some examples of that as we go through both these case studies. Now, throughout the first year, this is what I like to think we do differently compared to other OEMs is we work very closely with each utility. So we're meeting on a regular basis, sometimes monthly, sometimes biweekly, in order to try to carve out, what's a good strategy for that utility, right? There's going to be a aspect of getting comfortable with the technology, understanding the dashboard, figuring out what these notifications and things like that mean and how to act on that information. So we're meeting regularly with each utility to kind of figure out what's a good plan for them, right? And each utility is going to be different. And one of the keys here is you get what you put in, right? So both of the utilities that are with us today, they do an exceptional job at being proactive about these repairs, taking any information that they can get from the system, going out there and seeing if they can find these leaks and fix them before they become a bigger issue. So that's a huge part of it, right? We're trying to adapt. The utility is also trying to adapt the new technology. We learn a lot from this too. So we take a lot of the feedback we get, and that helps us kind of decide where we want to go as the next step, what we want to do with the technology, how we can make it better for utilities to use for leak detection. And then that's what we're talking about here. Right? It's building an effective strategy. And then at the end of the year, now informally, we're starting to kind of get more formal with this, but we really want to put together a summary of how did we do in the first year, right? What was the ROI on the units in the first year, whether it's water saved, reduction in the time to repair, whatever KPIs the utility is kind of focusing on, and then outline where do you want to focus on for year two. And areas here does not necessarily mean another area to put the units. It's more about what aspect of this whole program do you want to focus on? Do you want us to focus on? Do you want better leak detection, or do you want us to focus more on pressure monitoring for you guys and things like that, right? So we continue to meet with every utility beyond year one. Yeah, and I think it's because it's one of our differentiators. I think we get a lot out of it. I think the utilities get a lot out of it. So that's kind of just giving some insight into what year one looks like. So with that, let's go into King County. So this is phase one. So that area that was kind of on the west side of the map there. There's 1, 2, 3, 4, 5 units installed in this area. And monitoring started in January of 2025. So in that first year, there's 3 leaks that were repaired. One was a pre-existing leak. So number 1 here, and then 2 service leaks. One was a service leak here, and then one was a customer side leak, a large one in the 7th of October here. So we'll just go one by one through these, right? Starting with the first one. So this is a pre-existing leak. So what does that look like? So 22nd of January, we start collecting data from these hydrants, and then we can see 2 of these hydrants in particular, hydrant 4 here and 0601007, they're seeing a lot of signs of potential pre-existing leak. So we look at the acoustic data, we look at the signatures, we know what a leak looks like in different materials. But we don't have a lot of data on AC, right? So this is another kind of unique aspect of this deployment is we don't have a lot of experience with AC, but luckily a lot of the things do translate. So these 2 units in particular are saying, hey, there's a very good shot that you've got a leak already in the area, particularly this unit here, 0601, thinks that there's a leak very close by. So from that, we've determined if we've detected that there's a leak, we collect data for a few more days. And from that, the system has enough data to kind of figure out, where to find that leak, right? And this is something where, again, as we meet with the utilities, we might provide extra tidbits of information. We're looking at that data, we're analyzing that data each month. And so this is a search area that we can provide, say, look, a heat map sorts. If you're looking for that leak, right, go look for it. Here, it's most likely in this red area. If you don't find it, check some of these other areas along the street here, right? So that precise information is provided on the 29th of January. And then a little less than 2 weeks later, that leak is located and repaired, right? So the leak was actually right here. So 29 gallon per minute leak, this is estimated. Again, we really can't determine exactly what the flow rate was. This is a few pictures of the repair. You can see the clamp, right, on the leak there. So then we move on, right? So this is an interesting one. This leak actually started, we believe, on the 15th of April. So 0602004 over here starts picking up signs that there's a leak potentially nearby. It's actually a loud acoustic event that persisted for a few days. After that, we noticed that the leak activity near this hydrant has kind of gone up. And this is I would say, fairly common occurrence. You won't be able to go out and dig up every leak that is found immediately, right? There's a certain kind of threshold. The leak needs to be loud enough if you're going to go out with correlators, if you're going to go out with ground microphone to find this leak, depending on the pipe material, things like that, how loud your network is. There's a certain kind of minimum size, right, for that leak, and the conditions have to be right before that leak can be found and repaired. So this is one where we can detect it because we're inside the water column. We can hear that through the water. But you can see, so this is the acoustic event. So this is in April. That's kind of the baseline noise, leak energy or noise here. This is log scale, right? So this is actually, each tick is gonna be 10 times the previous one. You can see how this acoustic event was almost, it's 2 orders of magnitude higher than what their typical baseline noise is for this particular hydrant. And then after this vent lasted for a few days, we get the start of the leak. And you can see initially that this leak grows very, very slowly, right? This is between April and September. So at this point, it's impossible to find this leak, right? As it goes and goes, what we do in this scenario is we can monitor things like this, right? So on our side, if we're aware that, look, the system's picked up a leak, you go out, you look for it, you don't find it right away, and we keep tabs on it. We say sometimes the leak doesn't change for a very, very long time. We'll see that example as we get to the second utility. But in this case, we're seeing it steadily grow, right? So at some point, you're going to be able to go out, you're going to be able to find it. And that was actually in September, right? So we're monitoring that. You do the repair, you can see how that noise drops back to the baseline, right? But this is kind of one of those challenges, right? You can't find every leak. But again, if you're not proactive about going on looking for those leaks, you're never going to know, right? So 10th of September, that leak is right there. That's found. And here's kind of a photo of that leak, right? So not a huge leak. Again, on that service there, yeah, it explains why it's difficult to kind of hear this leak and pinpoint it right until it gets to a certain size there. Okay, one more. So this is 7th of October. So this is a very short leak, right? 17th of September, there's a big increase in leak activity detected by this hydrant here, right? Here's kind of what this looks like. Again, that leak energy, right? Here's the baseline, and then boom, there's a sudden jump, right? So for the last leak, it was kind of a slow, steady growth from baseline. This one kind of just started, and it grew a little bit over this period, but really it started quite loud, remained loud until it was fixed. And this was on the customer side service leak. So I believe the utility was able to actually just look at the billing data, the metering data to figure out and help pinpoint where this leak was, right? So very short um, leak, and that's kind of the goal, right? Is looking at a 3 week to 4 week kind of time span for the leaks that you can hear and you can actually pinpoint in the field. That's kind of a good target, given that a lot of these leaks will keep running without surfacing for very, very long periods of time, right? So 3 to 4 weeks to fix a leak is pretty good by that standard. That's where that leak was. So, what we want to do again is look at what's it worth, right? So we don't usually have exact data unless we've got the metered area and things like that, the flow. Um, Yeah, we can estimate. We've got the pressure close to that leak from the devices. We sometimes have photos or measurements from the leak, the crack before it's repaired. So from that, we're able to estimate, right? So a single reported leak or unreported leak, like the pre-existing one, the first leak we showed, it could be anywhere between $80,000 a year, right, in lost water revenue for the utility. Um, you know, because they're able to go out and find that leak right away, right? In just a few weeks' time, it only cost $3,000, right? So that's water saved. A lot of these leaks, again, they can run for a very, very long time. Depending on climate too, where we are, winter is break season, right? So a lot of these non-surfacing leaks, if you're unlucky, they start kind of in the spring and they stay non-surfacing until December, January, where they become breaks, costing even more money, right? So it's all the water that's lost throughout the year, and then the emergency repairs afterwards. So yeah, small leak can lead to quite a bit of ROI. And kind of another thing to note here is, this area, you keep seeing links, right? You find an area like this, you're going to keep seeing an ROI year over year. Just the likelihood that a pipe is going to break is going to be fairly high. So another key is picking areas like this, and that's where the planning comes in, right? We work with utilities to figure out where's kind of the best set of parameters for success within your network. Okay, so with that, I want to move on to the second utility, City of Waterloo in Ontario, and some facts about City of Waterloo. So it's located within the region of Waterloo, and City of Waterloo gets about 75% to 80% of their water from the region, and then the other 20 to 25% is groundwater from the Grand River. Serve about 1,000 or 137,000 customers, 440 kilometers of water main, and then average daily consumption about 36,000 cubic meters. Right, so here's kind of a layout of the water mains throughout City of Waterloo. And this is kind of an interesting case study for us because there's 42 units that were deployed throughout the City of Waterloo. So deployment actually started in 2019. I believe the city is one of our oldest clients, if not our oldest client. Um, and it didn't look like this before. So previously, these units were spread all throughout the network. The idea was to cover as much area as possible. Um, and what we learned over the years is you get more bang for buck, when you cluster the units in areas where you have a lot of non-revenue water issues, where you have a lot of breaks and things like that. Because ultimately, what we're good at with these units is leak detection, is early detection of leaks, right? Trying to find these leaks before they become breaks. So the closer you put the units, the better they're able to work together and triangulate. So what happened here is actually in 2025, it wasn't a new deployment, so to speak. We actually it looked at, which units can we take and basically redeploy into a single area. So this is an area here, Zone 4 West East, that has had a lot of issues with leaks and things like that in the past. We wanted to really double down on this area of the city and try to see, can we get on top of the water loss in this area. So we looked at which units can we leave around, and these units that are left around the network, again, they provide kind of key insights as to pressure and things like that. There might be, other critical assets around here. So leave some of the units to provide that coverage still. Move the remaining ones to get better leak detection in this area. So this is kind of an experiment here to see, is this going to work better than the previous layout? So we did that redeployment in March, late March. And the program, so we can say, in this case, the 1 year mark, so to speak, starts in March 2025, right? So what we did here is we looked at the acoustic data from all 31 units in the zone. And throughout April, May, we gave the city multiple areas of interest for further leak investigation. So we gave them quite a few, I think 6 or 7 different areas to look at, to do a leak survey. And the city was very quick to respond and go out and look for those leaks. And in the first 6 months, they found repaired 2 of these leaks here. And the challenge that you have in an area like this, and we'll see that with these 2 leaks, is when you're picking up multiple leaks, some of these hydrants are hearing multiple leaks, it becomes harder to find each individual leak, right? You're contending, the noise is coming from all different directions and it's trying to contend with one another. So when you fix one leak, it makes it easier to find the second one, right? But to kind of find and fix the first leak is the challenge. So I'll start with the first one here. So number 1 and 115 Christopher Drive, right? This is a pre-existing service leak. Again, pre-existing in this case is prior to us moving these units into this area. We believe that leak was already there. We didn't see a sudden change afterwards. So this was kind of a small pre-existing leak that started. And you can see this is from the UI that we have. We use kind of a color coding to differentiate and indicate how high the leak activity is for a particular hydrant. So the warmer the color, the higher the leak activity. It just means that you have a higher likelihood you've got leaks nearby, large leaks, multiple leaks, things like that. Right. So you can see this area is quite hot. Right. 881 here is pretty much maxed out. 46 is pretty much maxed out, and 51 is orange as well. This is a screenshot from the 21st of May. So actually, what happened is on the 6th of May, that small leak turned into a much larger leak, right? So there was an acoustic event, and then boom, we saw kind of a step change in the leak noise, particularly on 46, right? And so from that, we're able to develop a search area, right? So here's kind of a search area. It's, again, a fairly wide search area. We've got some hotspots, but again, kind of the challenge when you've got multiple potential leaks. We believe that there's more than one leak that's being picked up by these hydrants. So that leak actually ends up being here, and that leak was found and repaired on the 12th of June. So again, fairly quick response time, right, between the 6th of May being when that increase is actually logged by the system, and then a few days more for that data to come in to do the localization. And 12th of June, that leak is found and repaired. So what's that worth? Right. So again, this is a 1-inch service. It was a circumferential break. This is how we do our very scientific estimates. We look at the photo and we're guessing it's about 2 millimeters, 0.08 inches is the width of that crack, right? So from that, knowing the pressure, we're estimating it's about just under 10,000 cubic meters of water, right? So this leak ran for a little over a month. So we can use that number to kind of extrapolate, right? That, if a leak like this is allowed to continue to run without surfacing, right, you're basically going to be looking at $11,000 of lost revenue a month, or 10,000 cubic meters of water that is just going down the drain, right? So that proactive repair saves essentially saving you this amount, and also preventing that from becoming a break. You're finding this when it's good weather. You're not letting it run until winter when it can become a much bigger problem. But again, another one where, yes, there's a pre-existing leak there in March, but it's too small to actually pinpoint that leak, especially with other leaks in the area kind of contending with that leak noise. And you can look at it in other ways as well, right? So if you look at kind of the cost to basically produce that water, to pump it and supply it, right? The $11,000 a month or 10,000 cubic meters of water is equivalent to the annual emissions of 2,000 passenger vehicles, right? So you can look at it a number of different ways, but the savings are not small, even for a single service leak on a 1-inch line there. So another leak, this one is actually not too far away. So if I go back to the last slide here, 881 is here, right? So you can see where that Christopher Drive leak is. And now we're just kind of a little bit north west of where that last leak was. So in this area, we've got a few hydrants, 881, 134, 137. These are all saying, I've got something nearby, especially 881 and 134. So this is kind of the tricky part of this, right? So this is the search area initially provided for this leak, and you can see the hotspots are actually, they're not in the right spot, right? So the hotspot is around 881. There's another hotspot around 134. And this hotspot is because that Christopher Drive leak is pulling some of the predictions closer to 881, right? So what happens afterwards when that leak is repaired, right, we're able to give a much better prediction of where that leak is. So the leak actually ended up being here, 91 Mayfield, and they're able to find and repair this leak in October. But again, challenging leak to find and repair, right? It's again, a number of factors can contribute to how easy it is to hear a leak and find a leak with secondary kind of means of verification. Generally, yeah, bigger leak, is going to be easier to hear, but other factors might actually dominate over that, right? The pipe material, network noise, bury depth, things like that. So, the key is, that there's a leak, right? And keeping tabs on it. This one, I believe this one didn't grow much in size over the period. It's just very challenging to find this leak, right? So with the updated location information, I think the team was able to hone in and pinpoint where this leak was. So you can see here, right, this one ran for a bit longer. It's difficult to pin this leak, right? So leak didn't grow. It didn't make it any easier to find this leak between March and October. But the key here is this leak never surfaced, right? So, it would have kept going likely until at least the winter, where it would have became potentially a bigger issue, right? With the potential of becoming a break. So the city was able to find this leak before that a possibility could occur. And you can see again, even for another leak like this, right, the amount that you're saving each month in terms of water, in terms of GHGs. So that's it in a nutshell, right? What we really wanted to showcase was real examples with utilities And I just want to reiterate, right, that all of this is possible because the utilities that we work with are very proactive in what they do with the information, right? It only goes so far, and we know that no technology is perfect, and we want to work with utilities on that aspect too, right? Is to figure out what's working for you guys, what's the information that you guys need to go out and find these leaks sooner. And we've got two great utilities with us today that have helped make this work possible. So big thank you to Gus, to Scott, and to everyone else at King County and City of Waterloo for making all this work possible. If you got any questions, we're happy to take those now. Thank you.
Great. Thanks, Stan and Gus and Scott. Really appreciate you committing the time today, and also the time we've spent together working through your systems and trying to hunt down some leaks. So, easy question first. Somebody asked if we could share Gus and Scott's contact information. So if you guys want to if you're okay with that in the chat, if you just want to enter in your emails, then people will have those and can reach out to you directly. So one of the questions we did get, I'm going to sort of group it by the two utilities. So let's start with this one. This is my utility system is mostly ACP. I've been told by acoustical leak detection technicians that ACP can be harder to detect than plastic pipes. The leak example you show is a fairly high leak rate. How effective is hydrant AI at leaks in the lower 5 gallon per minute range?
You want me to take that, Tim?
Oh yeah. Yep.
Yeah, I think 5 is a good sweet spot for any material. So obviously, when you've got DI/CI pipe, it's going to be much easier to hear the leaks. The leak noise is coming through the pipe walls. When it comes to plastic, we've done a lot of research with plastic specifically, as we thought at the time, this would have been 2016 to 2020-ish, that plastic was the most challenging material for leak detection. It's also easier to get PVC pipe these days than it is AC, right? So could also factor in. But some of these leaks here, a leak like this, with the confining pressure of the soil, this could be something between 3 to 5 gallons per minute, right? But I think the fact is, regardless of what the pipe material is, when you have something that's less than 5 gallons a minute, it's a bit of a coin toss as to whether or not you'll be able to find it when you go out to listen for it, right? One of the things, again, we really try to focus on now is we understand that we're listening for the leak directly in the water column. We have the luxury of that direct, essentially, line of sight to that leak. Someone that's going out to verify that doesn't, right? They've got to go through all that soil, or they're listening through the pipe. And so we have to figure out for each utility, right, depending on what did they have available, what's their network configuration, the materials, what is that threshold, right? And we found that 5 is probably around the minimum in terms of being able to actually go out there with reliable success and find the leak. There have been smaller, but I would say 5 is probably the threshold, and I think 5. I don't think we have an issue seeing 5 gallons a minute in AC, but again, it also depends on how closely you space the units, right? So last thing I'll say about that is, that was kind of the driver for the work here in Waterloo, right? And this is possible because they already have so many of these units, right? So they're not purchasing 31 units. They're just repositioning a lot of these units. You can see the idea is to space them closer together. What you get from that is the closer you put the units, the smaller the size of the leak they're able to pick up and pinpoint, most importantly, because we can hear leaks from up to 3,000, 4,000 feet away. But in order to actually pinpoint that leak, if it's a small leak, if it's a small leak, the units need to be closer together, right? So that's really the trade-off. If you want to hear sub 5 gallon per minute leaks, you should probably space the units. We recommend somewhere between 1,000 to 1,500 feet apart.
Great. Thanks, Dan. Appreciate that. Ties in nicely to a couple of the other questions. One of them was when the leak was identified. So how closely can the Hydrant AI system actually pin a leak? And then what do utilities use? What City of Waterloo and King County using to verify the leak in the field? So Stan, why don't you start with how closely do you think we can pin a leak? with the technology. And then maybe Gus, you can talk about how you went out and actually field verified, and same Scott with you, if that's okay.
Yeah, I mean, in the past, right, we've gotten bullseyes before, right? I think at the end of the day, that's not the most important thing. I think it's giving kind of a clear scope to a utility, if they want to be able to go out, do an investigation in a few hours and determine yes or no, can I fix this leak? Can I find this leak? Right? What is that information, right? So it's more about, can you reliably get it within, let's say, 10 to 15 feet, right? A few sections of pipe, and reduce the amount of false positives you get, as opposed to trying to give it an exact set of coordinates. We're definitely not chasing that kind of accuracy. Again, a lot of what we do, and something I didn't really talk about today, is we we don't require much information from the utility in terms of GIS and things like that to actually operate the monitoring system. It benefits from that, but we don't need the pipe material, we don't need the pipe layout. Things can improve with the pipe layout, but a lot of what we do is we can operate in the dark. So inherently, we're in that scenario where a utility doesn't give us GIS, we don't have that available. There's only so much we can do, right, in terms of accuracy. So that's why we try to get within it, say 10 to 15 feet. If it's a big leak, yeah, sometimes you get the bullseye, right? There's been one in the past, I think for City of Waterloo, that we've looked at, actually just right here in the corner. That one was pretty much exactly where the leak was.
Yeah, as for Water District 90, they were able to give us a pretty high confidence pin in an intersection, where then we took our own leak detection equipment that we have in house out, which it's an LD12 like ground mic that you can listen through asphalt, and then it's got different attachments that you can listen on services or hydrants. Um, and then we also have our own correlator that we use, and then that kind of helped us pinpoint to get a little bit finer, uh, spot before we started cutting asphalt and digging. And it worked really well on the one that we did in that intersection. I think their high confidence leak was roughly 50 feet from where we then pinpointed it with our correlator down to like a 3x5 hole, and was able to find it that way.
And
Yeah,
Scott,
the
for the
same.
city, thanks.
Yeah, yeah, sorry. Same as Gus. We use correlators and loggers and just verify. Stan's team, they put us in a vicinity of where they think their leak is, and the accuracy is pretty tight. So we just use our own equipment just to verify and get ourselves within a few more feet.
Great. Thanks, gentlemen. Um, question here, and I don't know, Scott, if you want to take this one, or maybe I'll just answer it. So it was the City of Waterloo has a ton of units. How'd you buy them all at once? Or did you buy them over time? And, Stan referenced the fact there's 40 plus units, 42 units or so in the system. The City of Waterloo was one of our earliest utilities to work with us. And they actually went out and got a grant under the Canadian Water and Wastewater Fund. So that's a federal, provincial, and municipal funding. So the city provided some of the funding, but then the federal government and provincial government also provided funding at the same time. So we do have several municipalities and utilities that have been able to leverage local funding initiatives, which helps offset their capital investment in the system. And we're almost out of time, so I see one quick last question here. What is involved in relocating the units, time and specialty tools? Jeff, to relocate the unit, these units are located at the lower valve assembly of the hydrant. If you're in a dry barrel scenario, so you're actually having to pull that up, take them off the lower valve assembly, replace it with the previous valve assembly that was there, and then reinstall it. So the technicians that do this all the time, it's about a half an hour to install and about 20 minutes to take it out and put it back the way it was. Thank Gus and Scott and your teams at the utilities for joining us today. Stan, thank you as always for providing a really good overview of how the technology works and some of the things that the utilities have been able to find in their system and repair. For those of you who have joined us, thank you for giving up 45 minutes of your day today It is always a pleasure to be able to share information with the water community.